Today we're going to talk about section 8.3 in your textbook. So this section involves integrating functions that involve trig powers, specifically powers of sines and cosines. I want to start by reminding you of a few identities you learned back in pre-calculus. The first one's probably the most familiar to you, the Pythagorean identity, sine squared x plus cosine squared x equals 1. The second one you probably haven't seen in a while. This is the power reducing formula for sine. Sine squared x can be expressed as 1 minus cosine 2x all over 2. And the next one we're going to use is the power reducing formula for cosine. Cosine squared x equals 1 plus cosine 2x all over 2. You're going to want to have these memorized because we're going to use them quite a bit when we're working with these integrals. The integrals that we're looking at are integrals that are of the form sine raised to a power times cosine raised to a power, or some combination similar to that. So let's look at some examples and talk about the techniques we're going to use here. First example, we've got the integral of sine cubed x times cosine to the fourth x. What I want you to really observe here is that sine is an odd power, and that's important because since sine is an odd power, we can rewrite it as sine squared x times sine x. Now I put that sine x at the end, and you'll see why in just a minute, but make sure you see all I've done here is broken apart the sine cubed into sine squared times sine. And we have an identity we can use for sine squared x. Let's use the form of the Pythagorean identity that allows us to rewrite it in terms of cosine. So that sine squared became 1 minus cosine squared x, and we still have the cosine to the fourth and the sine. Then I'm going to just distribute the cosine to the fourth. What I want you to think about here, is there a u substitution we could make that will make this a little easier problem? If we let u equal cosine x, well, that works out nicely because the derivative of cosine x is negative sine x, and that's why I put that sine x at the end to make that substitution a little easier to see. So my new integrand just becomes the negative integral of u to the fourth minus u to the sixth du. Then we're just going to use power rules to integrate. So we have negative u to the fifth over 5 plus u to the seventh over 7. And of course, last step, we need to make sure we go back and replace u with the cosine x. That's our antiderivative. So in that last problem, both powers were positive integers, and this technique of splitting up that sine or that cosine and using a u sub will work as long as one of these powers is odd. So let's look at another example where we have an odd power. Here we have the integral of cosine cubed x over the square root of sine x. And this time, since the cosine term is odd, I'm going to split that and write it as cosine squared x times cosine x all over the radical sine x. And think about what identity we could replace cosine squared with to put it in terms of sine. So that cosine squared just became 1 minus sine squared x. Again, ask yourself, what u substitution could we make? If we replace u with sine x, again, that works out nicely because the derivative of sine x is cosine x. So my new integrand looks like this. If we just do a little algebra on this, don't overthink this. This is a real simple one. Just break this up in 1 over the square root of u minus u squared over square root of u. Rewrite it as powers, and then use your power rule. I'm going to skip some of the details here, but if we integrate, find the antiderivative for each of these, and then go back and replace u with sine x, this should be your final answer. Take a minute and make sure you see how I got that last step. Look at another example. This time we have the integral of sine squared x dx. So you'll notice, of course, there's no odd powers in this one. But think about those identities we talked about earlier in the presentation. We could replace sine squared x with 1 minus cosine 2x all over 2. And if we separate these, this is actually fairly straightforward integration. So we're just integrating 1/2 and then 1/2 times the integral of cosine 2x. Just think about a little mini u substitution here with this 2x. We get another factor of 1/2 that's going to go in front. So that 1/2 times the 1/2 factor becomes 1/4. Notice I just did the integral of 1/2, of course 1/2 x. So the integral of cosine u, sine u, but remember u was 2x. This is what those power reducing formulas are going to do for us when we have these expressions with even exponents. So let's kind of summarize what we've done here in these examples. If sine is odd and positive, you're going to want to save one sine factor and convert the others to cosines using identities. If the cosine term is odd and positive, you'll save one cosine factor, and convert the others to sines using identities. And then if both sines and cosines are even, use those power reducing identities to simplify. So let's do one more example using that third technique with an even power. Let's look at another one here. So here we have the integral of cosine to the 4th x dx. And since that's even, we're going to rewrite this as cosine squared x, quantity squared. So we had an identity earlier that we could use for cosine squared x, and if you'll recall, that was 1 plus cosine 2x all over 2, and this whole quantity then is being squared. So this is going to seem a little tedious, but essentially we're just going to multiply this out, FOIL it, break it apart, take a minute and do that so you see where I get the next step. If we expand this, we get 1/4 plus cosine 2x over 2 plus cosine squared 2x over 4. And of course, we could separate these, and the first two are pretty trivial to integrate. Now the last one, if you'll notice again, we've got a cosine squared term. So we're going to have to repeat this process a little bit and use the power reducing formula one more time to get rid of this cosine squared term. Now think about, since this angle is 2x, when we use the formula or the identity, and we double it, that angle will become 4x. So take a look. Make sure you see what I've done. I pulled the 1/4 to the front, and so cosine squared 2x becomes 1 plus cosine 4x, just doubling that angle, all over 2. And I'm going to skip the details here, but I want you on your paper to take a minute and make sure you see how to integrate all of this. These would be separated, and then we do u substitutions, and any like terms you have, you need to combine. Go ahead and pause the video and do that. When you're done, check it and make sure you see how I got this final answer.